So here's the titration problem to determine the concentration of a sodium hydroxide solution using 0.1 mole per cubic decimeter hydrochloric acid. This is a neutralization reaction. Let's look at the balanced equation. The alkali sodium hydroxide, NaOH, reacts with the acid HCl to form a salt and water, the salt being sodium chloride. What we do is to take a bulb pipette, typically 25 cubic centimeters or 25 mils. Here you see the liquid being run out, not blown out, just run out under gravity into the flask. Now there will be a little bit, as you see here, left at the bottom of the bulb pipette. Look what happens when you touch the surface of the liquid in the flask. By capillary reaction, roughly half of that is withdrawn. There still is a little bit left, and that's to be left. That has been taken into consideration during the calibration of the bulb pipette. Okay, you see here in the setup a burette with the conical flask below. Look at the bottom right, you'll see that the titrant, which is the technical name for the liquid in the burette, is 0.1 mole per cubic decimeter hydrochloric acid. Again, in the bottom right, you can see the technical name for the chemical in the conical flask is the analyte. In this case, it's the sodium hydroxide of unknown concentration. This is the titration between a strong acid and a strong alkali, and most indicators would do. In this case, I'm using methyl orange. Methyl orange changes from a yellow color in the alkali, in the flask, to an orange color at the end point. So you can see here over to the left, the hydrochloric acid is being run in, the stopcock has been opened, and I'm just rushing in the hydrochloric acid at this stage. We don't know how much it's going to take. All we're looking for here is a ballpark figure. Is it less than 10, more than 10, possibly more than 20? We're looking for a color change from yellow to orange. So 19's in at this stage, 19 coming up to 20. Just rushing it in, and again, look at the bottom left, shaking the flask all the time. As you begin to approach the end point, you'll notice it go from yellow to orange a little bit, but then go back to yellow. But eventually, it'll go orange and stay orange, and at that point, you should be ready to turn off the stopcock. And we read the bottom of the meniscus. You can see here, it's on 24.40. So we recorded the initial and the final readings. So our rough titer is 24.40. We're ready now to begin. We've got a good idea of where the endpoint is. So we now set out to obtain an accurate titer. You discard the chemicals in the flask and you rinse the flask with deionized water. Doesn't matter if there's a little bit of water left. And if you need to, fill the burette up and record the initial reading in your table. And off you go again. You know it's going to take probably at least 22 or 23. So there's no point in doing it slow to begin with. Just rush in the first 22 or 23 cubic centimeters of 0.1 molar hydrochloric acid. And when you get there, it's time to slow down and add it in a drop-wise fashion, even a half-drop fashion, using a wash bottle to wash off the half drop from the bottom of the burette, from what's called the jet, the bit below the stopcock. Now it may turn from yellow to orange, but go back to yellow again at this stage. Lots of shakings required, and you want to add enough, just enough, to make it go orange and stay orange. Look at the titer there. It's halfway between 23.8 and 23.9. So 23.85 I've recorded as the final reading, and the difference between the initial and final is the titer. So the first accurate titer is 23.85. Again, you empty out the contents of the conical flask and rinse it well with deionized water. Because a burette can measure out up to 50 cubic centimeters, you don't need to top it up again. We have enough in it to do the second accurate run. So the initial reading is 23.85. And again, you obtain an accurate titer. In this case, the final reading is 47.65. Take the difference between the initial and final, and we've got our second accurate figure, 23.80. Now these are actually concordant results, runs 1 and 2, because they're within 0.1 cubic centimeter. You could stop at this point and take an average between those two. But here we've taken a third accurate figure, or titer, and we now have 3 accurate titers. We do not include the rough run. We take those 3 accurate readings, add them together to get 71.45, and divide by the number of titers, namely 3. to get the average titer. Turns out to be 23.816. And if we round that up, as you see in the table bottom right, 23.82 is the average titer. So what do we do now? Here's how we calculate from those figures the concentration of the sodium hydroxide as required. So the indicator turned from yellow to orange. There are 3 steps to solve a titration question, just 3 basic steps. First, we need to get the number of moles released from the burette, the number of moles of hydrochloric acid. Second, from that we get the number of moles in the flask, the number of moles of sodium hydroxide in this case. And from that, lastly, we get the concentration of the chemical in the flask, again, concentration of the sodium hydroxide. Look at this rearrangement triangle at the top right-hand corner. You might find this of use. How do we express concentration, the concentration of any chemical? Well, concentration is expressed as the number of moles of chemical in a cubic decimeter. Concentration, moles per cubic decimeter. Here's how we use these rearrangement triangles, which are very useful. You see there that 1,000 cubic centimeters is 1 cubic decimeter. Okay, the rearrangement triangle. The rule is cover what you want and read what's left. So in step 1, we need to get the number of moles released from the burette. So you cover moles to see what moles equals. What's left? Moles is concentration times cubic decimeters. So what was the concentration of the hydrochloric acid? Remember, it was 0.1 molar. Standard solution with a concentration of 0.1 molar. We have to change the 23.82 into dm cubed by dividing by 1,000. So you move the decimal places you see here, 3 places to the left. And we get a figure of 0.02382. That's the volume changed from cubic centimeters to cubic decimeters. So moles is the concentration times the volume in dm cubed, and that's what it works out to be, 0.002382 moles of hydrochloric acid. We've achieved step 1. We've worked out the number of moles released from the burette. Next, from that, we can elucidate or work out the number of moles of sodium hydroxide that must have been present in the flask. Look at the equation. 1 mole of sodium hydroxide reacts with 1 mole of HCl. Where there's no number in the balanced equation, it's taken to be 1. They react, we say, in equimolar amounts or equimolar amounts. So whatever number of moles of hydrochloric acid was needed from the burette, obviously we must have had the same number of moles of sodium hydroxide in the flask. So there you have it, we've achieved step 2. Lastly, from that we can now get the concentration in the flask. Cover what you want if you want concentration. So concentration is the number of moles divided by the volume in dm cubed. And we have those 2 figures. We've just worked out the number of moles of sodium hydroxide in the flask, 0.002382. What was the volume of sodium hydroxide we took using the bulb pipette? Well, that was 25 cubic centimeters. But once again, it needs to be changed to dm cubed by dividing by 1,000, or moving the decimal place 3 places to the left. So that's 0.025 dm cubed. So we work that out, and it comes out as 0.09528 moles per cubic decimeter. We used to refer to that as a molar solution with the unit capital M. So there you have it, the concentration required. Concentration of sodium hydroxide turned out to be 0.095 mole per cubic decimeter.